prestressed concrete members. What are the various types of losses occurred in pre-tension members as well as in post-tension members? What are the formulas to calculate the various types of losses? And then we will illustrate those formulas with the help of one example. So the learning objective of this session is students will be able to analyze various losses in the prestressed concrete members which are pre-tensioning as well as post-tension. So these are the types of losses which do occur in pre-tensioning and post-tensioning process. So in the pre-tensioning, shrinkage loss, creep loss, elastic shortening, relaxation of steel. These four losses are occurred. In post-tensioning, shrinkage loss, creep loss, relaxation of steel, anchorage loss and friction loss. These losses are occurred. But in the post-tensioning beams, if all the wires are tensioned simultaneously, then there is no loss due to elastic shortening. But all the steel wires are tensioned one by one successively, then there will be the loss of elastic shortening. Now losses computation formulas. So shrinkage loss. The shrinkage loss of concrete in prestressed members results in the shortening of steel wires. So the shrinkage loss can be calculated as shrinkage loss is equal to ECS into ES, where ECS is the shrinkage strain and ES is the modulus of elasticity. For the pre-tensioning and post-tensioning, the values of shrinkage strain are different and they can be computed as, for pre-tensioning it is 300 into 10 raised to minus 6, and for post-tensioning it is ECS is equal to 200 into 10 raised to minus 6 divided by log to the base 10 T plus 2, where T is the age of concrete. Now the creep loss. So creep of concrete or creep loss. The creep of concrete means deformation of concrete which depends upon the interval of the time to which the member is loaded. So the creep loss can be computed by two methods. It is ultimate creep strain method and creep coefficient method. So both are having their formulas to calculate the creep loss. So the ultimate creep strain method. So creep loss is equal to EC into FC into ES. So EC into FC into ES. EC means what? The creep strain. Okay. So EC is the ultimate creep strain. FC is the stress in concrete at the level of steel, and ES is equal to modulus of elasticity of steel. Creep coefficient method. So in this, the formula is creep loss is equal to phi into M into FC, where M is the modular ratio and it can be taken as the ratio of Young's modulus of steel to the Young's modulus of concrete. Then phi is the creep coefficient. FC is, again we have already seen, stress in concrete at the level of steel. Then M is the modular ratio and EC is the Young's modulus of concrete. So FC is the stress in steel, stress in concrete at the level of steel, where the steel is placed at that level. What is the stress in concrete? That is represented by this FC, and it is calculated as P naught upon A plus P naught into E square by I, where P naught is the initial prestressing force, E is the eccentricity, I is the moment of inertia. So the phi, that coefficient phi, this phi value, creep coefficient phi, this phi value is given in the IS code, IS 1343, and from that this table is taken. So when the age of concrete is 7 days, 28 days and 1 year, the creep coefficient phi, it is calculated as, the values are given in the table as phi is equal to 2.2 for 7 days, 1.6 for 28 days, and for 1 year it is 1.1. So relaxation of steel. The steel also possesses the property of creep. It basically varies from 1% to 5%. Normally it is taken as 3% of initial prestress or 5% of initial prestress. So 3% of sigma naught or 5% of sigma naught. That is the relaxation of steel we normally take. Then elastic shortening. So elastic shortening can be calculated as M into FC, where M is the modular ratio which we have already seen, the ratio of Young's modulus of steel to the Young's modulus of concrete. FC is the stress in steel at the FC is the stress in concrete at the level of steel. Okay. So in this way we can calculate the elastic shortening, loss due to elastic shortening. Then anchorage slip. So the loss due to anchorage slip, it can be calculated as ES into delta upon L, where L is the length of cable, delta is the slip of anchorage, and ES is the modulus of elasticity of the steel. Next is the friction loss. So friction loss can be calculated by this formula, mu alpha plus kx into sigma naught, that is initial prestress. So here you can see alpha is the cumulative angle, mu is the coefficient of friction, sigma naught is the initial prestress, k is the wave effect coefficient, and x is the span. And here the notable thing is, in this formula we need to put x span in meters. So we need to put the value of span in meters while calculating the friction loss. Now we will illustrate this with the help of one example. We will take this example. So example is a prestressed concrete beam 200 mm by 300 mm in a section is prestressed with high tension steel wires of an area 320 mm square located at an eccentricity of 50 mm. The initial stress is 1000 MPa, span is 10 meter. Calculate percentage loss of prestress. So we need to calculate the loss of prestress if the given beam is to be considered as a pretensioned, and second, if the same beam is considered as a post-tensioned, and the various values of constants are given, such as Young's modulus of steel 210, Young's modulus of concrete value is also given, K is also given, then creep coefficient, that phi value phi is also given, relaxation loss of steel, it is stated as 5%, then shrinkage strain, anchorage slip is given as 1 mm, shrinkage strain is 3 into 10 raised to minus 4 for pre-tensioning and 2 into 10 raised to minus 4 for the post-tension. So this is the given data in the problem. So we know that the cross-sectional area we can calculate as the dimension is known to us. From the dimension again we can calculate the moment of inertia of the section also. Here area of steel is also given 320 mm square. Then eccentricity is also given 50 mm. Initial stress is 1000 MPa, so the value of sigma naught is given. Initial stress is sigma naught, and the span is 10 meter. So based on this we will move further to get the answers. So now the moment of inertia, we know how to calculate that. It is BD cube by 12, as it is a rectangular section. 200 by 300 is the dimension. So BD cube by 12. So if we put the value B into D cube by 12, we will get the moment of inertia as 450 into 10 raised to 6 mm raised to 4th. Then pre-stressing force. So we know the basic formula. Stress is equal to load upon area, or force upon area we normally took. So if we want to calculate the load or force, it will be stress into area. So similarly, prestressing force, initial prestressing force P naught is equal to initial prestress, that is sigma naught, into area of steel, that is AST. If we put the value prestressing force P naught is equal to, so sigma naught is given as 1000 MPa in the problem. So 1 MPa is equal to 1 Newton per mm square. So we have put that value as it is, 1000 into area of steel is 320. So if you compute this, it will works out to be 320 kilonewton. This is our initial prestressing force. Now modular ratio M, it is calculated as ES upon EC. It is 210 divided by 35, which works out to be 6. Now pretensioning. So first we will consider the beam as a pretensioning beam. So we will calculate the value of FC. The FC is nothing but stress in concrete at the level of steel. So the formula just we have discussed previously. The formula for FC is P naught upon A plus P naught into E square by I. So we just need to put the values in the formula. We already have all these values. So this is 320, which we have calculated already here, 320 kilonewton. Then area 200 by 300. Again eccentricity E value, it is 50, and I we have already calculated 450 into 10 raised to 6. So after doing all the calculations, this value of FC, that is the stress in concrete at the level of steel, it works out to be 7.11 Newton per mm square, that is MPa. So now the shrinkage loss, we have gone through formula already. So it is shrinkage strain into Young's modulus of steel. So the value of shrinkage strain, it is given in the problem, 3 into 10 raised to minus 4. This value, it is actually given in the problem. This value is also given in the problem. So we put both the values over there, and we got this value, shrinkage loss 63 MPa. Newton per mm square. Similarly, the value of creep coefficient is given, so creep loss can be calculated as phi into m into fc. So phi into m into fc, so here we need to put the values. So phi is 1.6, m we have already calculated 6, and fc value is 7.11, and this loss is works out to be 68.24 Newton per mm square. This is our creep loss. Similarly, relaxation loss. The relaxation loss is equal to 5% of initial prestress. So initial prestress is nothing but sigma naught, and which is given as a 1000 for this numerical. So now relaxation loss is 5%, means what? 5 by 100 into 1000. 1000 it is already given in the problem. So relaxation loss is works out to be 50 MPa. Relaxation loss is works out to be 50 MPa. Then elastic shortening, it is calculated by using the formula m into fc. So elastic shortening is equal to m is 6, fc is 7.11. If you do the calculation, you will get 42.66 as a loss due to elastic shortening. So now total loss. So add all the losses up till now which we have calculated. Shrinkage loss, creep loss, then elastic loss due to elastic shortening, relaxation loss, all the losses are added together and we get the total loss, and that value works out to be 223.9. So the total loss is 223.9 MPa. So total percentage loss. So now the percentage loss is calculated as what? It is 223.9 divided by 1000. So the loss quantity is 223.9. Initial was 1000, which is already given in the problem, 1000, and into 100 to get the percentage. So it is 22.39%. So in the pre-tensioned member, the total losses during this prestressing procedure, it occurs to be 22.39% for this numerical, for this given values. Now similarly, if the same beam, if we considered it as a post-tension beam, then the shrinkage loss ES, it can be calculated as shrinkage strain into ES. So that values if we put, we get the shrinkage loss as 42 MPa. Similarly, creep loss, again the same formula, phi into m into fc. If we put all the values, we get creep loss as 68.24. Okay. Then relaxation loss, it is again 5%, it is given. So that the same relaxation loss, it can be calculated. It is 50 MPa after the calculations. Anchorage slip, the anchorage slip, if we put the value, ES is 210 into 10 raised to 3, delta it is given as 1 mm is the slip, and L is the span is 10 meter. So convert that meter into mm, so 10 raised to 3 is there. So anchorage slip works out to be 21 MPa. Then friction loss, it is mu alpha plus kx into sigma naught, that is initial prestress. So here the value of mu is alpha is 0, so this term will become 0. So what will remain? It is kx into sigma 0, that is initial prestress. Now the friction loss, it is calculated as the value of k is given in the problem, x is the span in meters. So here you can observe we have written only 10, so it is kept in meter, and sigma naught, it is 1000. So friction loss is works out to be 15 MPa. And now the total loss. The total loss will be the addition of all the losses, and it is 196.24. So the percentage loss. So the total percentage loss will be 196.24 by 1000 into 100. So it works out to be 19.62%. So now we observed that for post-tension member, the loss is 19.62%, and for pre-tension member, the loss is near about 22%, 22.39 something percent. So the losses in the post-tensioning members are less as compared to the pre-tensioned members. And these are some references for this prestressed concrete.